Welcome once again, and as you know, in previous some videos we are doing the chapter nets and filters from topology, and I'm continuing the same here in this video. So the first theorem what I'm going to do today is write down the statement of the theorem first, and then as usual we will move on to the proof. So let X top be a topological space and let Y be a subset of X. A point X naught of X is a limit point of Y if and only if there exists a net in Y minus the singleton set X naught that converges to X naught. So this is the statement of the theorem, and here once again we are having if and only if. So direct proof will be needed, as well as the converse of this theorem is also true, so we will have to prove converse as well. So first I'll suppose that the point X naught is a limit point of Y, and then we will show that there is a net in Y minus X naught that converges to X naught, and then we will move on to the converse. So let us start the proof now. So let X naught belonging to X be a limit point of Y. Let it be a limit point of Y. Then definitely, since X naught is a limit point of Y, every neighborhood of X naught will have at least one point of Y other than X naught. So that means, this means for every n belonging to nx naught is the neighborhood system of X naught, that means the collection of all possible neighborhoods of X naught, and you take any neighborhood n from that collection. For every n belonging to nx naught, n intersection with Y minus X naught is non-empty. That means this neighborhood contains a point of Y other than X naught. Let that point be Xn. Let Xn belongs to n intersection Y minus X naught. Let this be the point Xn. Now we want to have a net in Y minus X naught that converges to X naught. We know that nx naught, the neighborhood system with binary operation subset of, is a directed set. This I have explained in a previous video. This is a directed set. So define f from this nx naught, that means the directed set nx naught d to Y minus X naught, because we want the net in Y minus X naught. So I'll have to take Y minus X naught on the other side. So define f from this to this as f of, now nx naught will have members of the type neighborhoods of X naught. So let it be n. So f of n, and we know that for every n, this xn belongs to n intersection this. So this xn belongs to n, and this xn belongs to Y minus X naught also. So I'm defining it as xn. Now in a previous theorem we have proved that this net will converge to X naught, whose neighborhood n we have taken here. So I'm directly going to write here, I'm not going to explain once again. So therefore this net f converges to X naught, and this net is in Y minus X naught. So there is a net in Y minus X naught that converges to X naught. So the direct proof is over, and now we will move on to the converse. Conversely, let there be a net in Y minus X naught that converges to x naught. So let there exists, so I'm starting the proof here now. Let there be, I'm omitting the rest of the part because it is the proof now. Earlier it was just part of statement, now it is the proof. Let there exist a net in y minus x naught that converges to x naught. And we want to prove that, x naught is a limit point of, x naught is a limit point of y. This is what we want to prove. Now, there is a net in y minus x naught that converges to x naught. Let the net be f and let the corresponding directed set be d. So let f from d to y minus x naught be the net that converges to x naught. Let this be the net. By the definition of convergence of net, for every a naught, there exists a naught in D such that for every a greater than or equal to a naught, that means if a follows a naught, what we have? We have f of a belongs to, this is a net, and we will have to take some neighborhood first. So for every n belonging to an x naught, there exists a naught in D such that whenever a follows a naught, your fa belongs to n. And we know that a naught follows a naught. This is true because of the first property, the definition of directed set. The first one is that a is greater than or equal to a. That means a follows a. That means a naught is following a naught. And whenever a is following a naught, your fa is in n. So if a naught is following a naught, then fa naught must be in n. So this means fa naught is in n. Also, your net is in y minus x naught. That means every image of member of D under F is in y minus x naught. So this means your f of a naught also belongs to y minus x naught. So fa naught belongs to n, fa naught belongs to y minus x naught also. So that means your n intersected with y minus x naught, this is not phi, because at least fa naught is the element which is a member of both of these sets. So this intersection is not phi. And if n intersection, this is, and what is n here? N was arbitrary neighborhood of x naught for every n. So this is true for every n belonging to an x naught. So for every neighborhood n of x naught, we are having that neighborhood intersected with y minus x naught is not phi, and this means x naught is a limit point of y. So this theorem is being proved, and now we are moving on to another very interesting theorem, which is basically a very good connection between the topic nets and filters and Hausdorff space. We know that when we talk about sequences, a sequence converges to a unique point. And in the previous video I have told you that a net need not converge to a unique point. It may converge to many points, and in fact it may converge to infinitely many points. And now if this is a case of a Hausdorff space, then the situation changes and the net converges to at the most one point. That means either it is not convergent, and if it is convergent, it will converge to exactly one point. So the convergent point of convergence will be unique if the net is convergent. So this is the theorem what we are going to do. So write down the statement of the theorem. First, let x top, don't start with let x top is a T2 space, Hausdorff space, if and only if every net in X converges to at most one point. At most one point means either it converges to a point, otherwise it is not convergent. So if it converges, then it converges to a unique point. So in this case, the uniqueness of point of convergence will follow if your topological space is T2. And once again, here you are having if and only if. That means the direct proof we will have to give, we will also have to give the converse proof of this theorem, as the converse is also true. So I'll take the two parts one by one. First I'll suppose that this is the Hausdorff space, and then I'll show that it converges to at most one point. It cannot converge to two distinct points, and then we will do the converse. So I am going to start the proof. Be ready for that. Let X top be a T2 space, and now we are to prove that every net converges to a unique point. Let there be a net, on the contrary, let there be a net which converges to two distinct points. Let f from some directed set D with some binary relation obviously that follows or greater than or equal to, let f from D to X be a net in X such that f converges to X and f also converges to Y where X is not equal to Y. Now X is not equal to Y and your space is Hausdorff. So that means there must exist open sets G and H, G containing X and Y containing H containing Y, such that G intersection H is Y. So since X is not equal to Y, there exist open sets G, H such that X belongs to G, Y belongs to H, and G intersection H is phi. Now G is open set and X belongs to G. That means G is a neighborhood of X and net converges to X. So therefore, for every neighborhood, or you can say F is eventually in every neighborhood. F is eventually in every neighborhood. Since F converges to X, we have that F is eventually in every neighborhood of X. In every neighborhood of X. And G is also a neighborhood of X. So this means F is eventually in G. And F is eventually in G means there will be some stage A naught such that whenever A follows A naught, your FA belongs to G. So therefore, there exists A naught in D such that for every A that follows A naught, we have FA belongs to G. And now I am changing the situation that H is also open set and Y belongs to H. So H is a neighborhood of Y now. H is a neighborhood of Y. Since F converges to Y, we have that F is eventually in every neighborhood of Y. F is eventually in every neighborhood of Y. So one neighborhood of Y is H. So F must be eventually in H. So F must be eventually in H. That means there will be some A naught dash, you can say. There will be some A naught dash in D such that whenever A is greater than or equal to A naught dash, we have our FA belonging to H. And now, the most interesting part of this theorem. Now the most interesting part of this theorem is there. A naught is in D. A naught dash is also in D. A naught is in D. A naught dash is in D. And by the definition of directed set, definitely there exists some B in D such that B follows A naught and B follows A naught dash. That is the third part in the definition of directed set, that if there are N and M in P, N and M in D, then always there exists P in D such that P follows M, N and P follows M. So that P I'm naming here as B. So there will be some B in the directed set D such that B follows A naught and B follows A naught dash. Now, if your A follows B, if A follows B, then A follows B and B follows A naught, means A follows A naught, because of the second part in the definition of directed set. If your A is following B and B is following A naught, then A following A naught. And if A is following A naught, then you know that for A following A naught, your FA belongs to G. That means FA belongs to G. For the same A, suppose I am taking the same A, now A follows B and B follows A naught dash. So this means your A follows A naught dash. And if A follows A naught dash, then your FA belongs to H. So this means your FA belongs to H. So what is the conclusion? The conclusion is that for every A that follows B, we have our FA belongs to G as well as to H. That means FA belongs to G intersection H. So there are many FAs in G intersection H, which is a contradiction because G intersection H is phi. In an earlier step you have written G intersection H is phi, and now we are saying that FA belongs to G intersection H whenever A follows B. So this is a contradiction, and this is a contradiction because we have supposed that this is we have supposed that it converges to 2 points. So it cannot converge to 2 points. The every net in X must be convergent to at the most 1 point. So first one side of the proof is complete, and now we are moving towards the proof of the converse part of this theorem. So conversely, we will suppose that every net, conversely, suppose every net in X converges to at the most 1 point, and what we are to prove that now? We are to prove that our space X tau is a T2 space, is a Hausdorff space. This we are to prove. Suppose on the contrary that it is not a Hausdorff space. Suppose, if possible, X tau is not T2. X tau is not T2. Then if you take two distinct points X and Y, definitely every neighborhood of X will intersect every neighborhood of Y, because if even a single neighborhood of X is not intersecting neighborhood of one particular neighborhood of Y, then that N intersection M will become phi, and that will make the space Hausdorff, and we have supposed that the space is not Hausdorff. So this means for every X not equal to Y and for every N belonging to NX, M belonging to NY, N is a neighborhood of X, M is in the neighborhood of Y, N intersection M is not phi. This is because we have supposed that the space is not Hausdorff. In the Hausdorff space, there must exist at least one neighborhood here and at least one neighborhood here whose intersection is phi. Now since the space is not Hausdorff, for every neighborhood here and for every neighborhood here, their intersection will be not phi, will be non-empty. Now, if this intersection is non-empty, definitely there will exist some element, and I'm naming that element as x and m. So let x and m be the element that belongs to n intersection m. Now nx and ny. Nx is the neighborhood system of x, ny is the neighborhood system of y, and we know that nx with the binary operation subset of and ny with the binary operation subset of are both directed sets. And if we are having two directed sets d1 and d2, then their Cartesian product also becomes a directed set. So I am taking their Cartesian product. So let P be nx Cartesian product with ny, and define this binary relation on P as this I am defining as nm, n1 m1, you can say n1 m1 follows n2 m2 if and only if your n1 is a subset of n2 and your m1 is a subset of m2. So in this way, using the two binary operations of nx and ny, for nx binary operation is this subset of, for ny this subset of is the binary operation. Using these two binary operations, I have defined the binary operation on the set P, which is the Cartesian product of nx and ny. So then this P with this newly defined binary operation is a directed set. And now if I define some function from P to some set, then definitely that will be a net, because the domain will be a directed set. So define f from P to x as f of, now P is nx cross ny, so its members will be of the type some member here and some member here, their ordered pair. So f and m, and we are defining f and m. Now n and m are there. N is a neighborhood of x, m is a neighborhood of y, and we know that there is a point x and m that belongs to an intersection m, and that point I am defining here as the image of this ordered pair nm. So this is x nm. This point is the image of nm. This we have defined, and now we will show that this net converges to x as well as actually there may be some confusion in this x and this x. So better if you replace this x by some other notation, take it as znm. So this x and this x will not be confused. So take z here instead of taking x, take znm. Now I will show that this net f converges to x as well as to y. This we will prove. So how that can be proved? Let u be a neighborhood of x and v be a neighborhood of y. Then for every linearly ordered pair nm that follows the ordered pair uv, what we have f and m is equal to, by definition it is znm, and znm we know that it belongs to n intersection m, And since Nm follows UV, your N is a subset of U and M is a subset of V. So N intersection M will be a subset of U intersection V. So that means Fnm belongs to U and Fnm also belongs to V. So you can say Fnm belongs to U for every Nm that follows UV. So that means this UV is the stage. After this stage, whenever Nm follows UV, your Fnm belongs to U and this U is a neighborhood of X, and this means your net converges to X. Similarly, this Fnm, now Fnm belongs to U intersection V, so it also belongs to V. So this Fnm belongs to V for every Nm that follows UV, and once again UV is the stage. Whenever your Nm follows UV, your Fnm belongs to V and this V is the neighborhood of Y, and this is true for every neighborhood. So your net F converges to Y also, and this is a contradiction because we have given that a net in X can converge to at the most one point. How it can converge to two distinct points? So we arrive at some contradiction, and this is the contradiction because our supposition was wrong. And what we have supposed that our space X tau is not Hausdorff, which is wrong. So X tau must be a Hausdorff space. So here the theorem is being completed, and I'm going to stop this video here. In the next video we will have more and more theorems on nets, and then we'll start filters. Thank you. Till then, thanks once again.